Hi everybody, let's talk about mode orthogonality. So remember in our earlier lectures, we derived this general expression for the electric field profile in a parallel plate waveguide. And it wasn't exactly a precise solution either. We got this sort of general class of solutions that are kind of very interesting in their behaviors. The superposition of these individual little modes, which means a full and complete solution for this E field here depends on knowledge of all of these coefficients. So most of this we know. For example, I can excite a waveguide with an arbitrary frequency, so I have control over this parameter here, which then determines these allowed solutions over here for each of these individual modes. The only thing that's left over are these mode amplitudes, okay, which generally scale with the nature of how you excite the waveguide. So there's basically two ways to kind of think of this problem here. One is you think of it as the following. Suppose I give the coefficients here, a sub 1, a sub 2, a sub 3, dot, 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 all the way out to infinity. Find the electric field. Okay, and this has a special name in mathematics. We call that the forward problem. Right? So if I'm given these coefficients, I know what all these other little constants are here, then I can then perform this summation, just grind on it. You give it to MATLAB and it'll run all the calculations and it will then have an electric field profile at the end of the day. And I've shown you some nice little demo videos where I do exactly that. I show you how each mode looks, and then I even uploaded one where I just randomly picked a bunch of values for my a sub n here, and then added them all together to get some weird blob of energy going down a waveguide. There's also another way to kind of think of this problem, and that is, suppose you are given the electric field instead, and I ask you to find the coefficients, a sub 1, a sub 2, dot, 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 out to infinity. So in mathematics, this also has a word. It is called the inverse problem. Like so. So the way you can think of it is one possible way to work this mathematically is say, given all of this stuff here, calculate that here. Or alternatively, I could say, given this thing here, calculate the coefficients over here which gave rise to it. And both of those problems are often very important in mathematics because you gain a lot of insight into things when you get comfortable with going backwards and forwards. So we're going to talk a little bit about how to unpack these coefficients if I am given the profile over here. So the way it works is, first things first, I'm just going to let z equal 0 because the actual location of my z doesn't really change a whole lot, right? If I set z to a constant value, then this thing here becomes just some complex number, which I can sort of treat as just a lumped factor into this leading coefficient anyway. So it really doesn't matter where I define my 0 point. I can still unpack these modes. So in your mind, just here's the waveguide, and you just pick a little cross-sectional slice down it here. So like z equals z naught. And wherever I put this little slice shouldn't really matter. Each slice contains just as much information as every other slice because all of the same coefficients will give rise to it. The only difference that happens when I move this left or right is that this little phase term changes, which you can assume if it's 0 would just be manifest as changes in this constant anyway. So we might as well just say 0 here so that this disappears because the actual location is fundamentally kind of arbitrary anyway. So I'm going to define a function f of y is equal to e sub x, the x component of my E field, of y comma 0. So this is just to make my notation a little cleaner. And you notice I don't have to keep track of this little vector here because we know that the electric field is polarized in one direction, so we don't have to keep explicitly writing this out. So what I will get is the following. The summation from n equals 1 to infinity, a sub n sine of gamma sub n y. And again, this is true at any arbitrary location in z because whatever this complex exponential does over here, it would just appear as if it's a phase shift on this coefficient no matter where this location is. So this is a Fourier series. you look at that and immediately, Fourier series. You look at that, that should immediately jump out at you and say, oh, that is a Fourier series. I know how Fourier series behave. They obey all sorts of wonderful properties that are inherent to vector spaces. And in fact, this sort of Fourier series is a complete basis in that I can span the set of all continuous functions along y. So literally any function here I place into this, if it's continuous, and probably even some discontinuous ones, I can create a Fourier series that goes with it. There's a unique Fourier series that will create that function. So you'd say it spans, so that's a fancy word in linear algebra. This little series here spans all continuous functions along y. So due to the properties of the Fourier series now, if I know y, I can derive the actual coefficients here, a sub n. So it works like the following. First things first, I'm going to take f of y, and I'm going to multiply it by some random mode here, mode profile, gamma sub m. So you notice that would become the summation from n equals 1 to infinity a sub n sine of gamma sub n y times sine of gamma sub m y, like the following. So all I did was multiply both sides by this term. I'm now going to integrate both sides like so. From 0 to d, dy, dy, 0 to d. If I do it to one side, I can do it to the other. And for further kicks and giggles, because I have the power of foresight, I'm going to multiply by a 2 over d, like so. So why am I doing that? Well, the answer is very simple, because this little summation here is going to simplify tremendously. So I'm going to flip-flop the summation with the integral here, and I'm going to get the summation from n equals 1 to infinity, a sub n, and I'm going to get a 2 over d times the integral from 0 to d of this guy here, sine of gamma sub n y, sine of gamma sub m y dy, and we can do that because the integral is a linear operator, which means it doesn't matter where I put the summation in here. So this is a very, very important and special integral because this whole thing here, including that little factor there, evaluates to delta n m. So if I don't include this little coefficient, what you actually get is a d over 2 here times delta. So I multiply by this 2 over d to cancel that out, and I get just delta n sub n, which means this thing looks like the following. It'll be 1 if n equals m and 0 otherwise. So all of these terms in this summation are going to be 0 except for only one value, and that is when n equals m. Otherwise, they all disappear and annihilate and kill each other in this little integral. So this whole thing evaluates to simply the mth coefficient. So I have all these summations, or all of them, and this little integral is singling out the mth one. So what that means now is we'll just rewrite this down here. A sub m is equal to 2 over d times the integral from 0 to d f of y sine of gamma sub m y dy. Okay, and this is true for all m. Right, so m is equal to 1, 2, 3, ... all the way up to infinity. So if I am given this function here, I can now unpack all of the little coefficients that would give rise to it. And you can cross-check that if I am given this, I perform this, I can derive all of these, and then I can plug them all back up into this to recalculate my profile, and I should then replicate this original function here. So that is the power of mode orthogonality and how it allows you to derive each individual coefficient if you are given some function within this waveguide. And so just to kind of give you an idea of how that's useful, as you can imagine, this waveguide here, suppose I am exciting it with some wave, which means there is some electric field here distribution that's going to fill this little waveguide here. And you also have to account for the reflections here, but if you just simply equate all of that stuff together, you essentially get the profile down at that particular point at the entrance to the waveguide. And then all of the modes can be calculated using this expression here, and that tells me all of the field profile down into the waveguide here. So this little property essentially allows me to kind of figure out how this waveguide will behave if I excite it with some particular little profile here. Okay, so that is mode orthogonality in a nutshell. Just remember, this equation here is the key insight.